Section 5.4 Logarithmic Equations. So this is what we are working towards. We studied inverse functions and we studied exponential functions, and then we found that the inverse of exponential functions were log functions, and then we studied some log properties. So now we want to take all of that information and apply it to actually do something useful. So in this case, we're going to actually study, in this section, we're going to study how to solve logarithmic equations. Okay, they're equations that have log terms in them. Alright, and we're also going to study another type of equation, exponential equation. Okay, and I'll explain why they fall under this category too. Okay, so let's take a look at what we want to do here. Okay, so we're going to solve equations in this second. So our goal is to solve equation. When we studied log functions in the last section, I told you two things. I said to remember logs are inverses of exponential function. The other thing is always remember in the future, if you're solving an equation and the unknown is an exponent, then the only way you can solve that is by introducing logs. So we're going to take a look at a couple different types of equations. The first one is exponential equation. In this case, the unknown is an exponent. Okay. Then we're going to take a look at solving log equations. I'll abbreviate that with one term, one log term. Then we're going to take a look at solving log equations with two log terms. And then we'll end the section by taking a look at log equations with three log terms. So you can see there is a few different types of equation, and then I will end this section by doing a problem that's quite a bit more challenging and doesn't fall under any of these categories, but it involves logs. Okay, so let's take a look at the first type of log problem. So we are talking about exponential equations. Okay, this is where the unknown is an exponent, and this is one great use of logs. Anytime you have an unknown exponent, we always want to introduce logs. So what we want to do is, in this case, the way we solve that is by introducing logs on both sides. Okay, and then we just solve for x like we normally do. Okay, so that's the trick, and you can introduce logs of any base. I always prefer using base e. That's just my preference, but you can use whatever base you want. Sometimes it's easier to use a certain base over other bases. Do you guys follow? But it's completely up to you how you want to do that. Now let me start off by doing a trivial example where you really don't need to introduce logs. Like, for example, if I gave you 3 to the 2x minus 1 is equal to 27, and I ask you to solve this for x. Okay, now why don't I need logs here? Well, that's because technically I can write this 27 can be written as a power of 3, which is 3 to the 3. Okay, I have two exponential numbers that are equal, and exponential numbers like log 1 to 1, the only way they are going to be the same is if this exponent is equal to this exponent. So this implies that 2x minus 1 is equal to 3, so we get 2x is equal to 4, so x is equal to 2. So there's your answer. So this was a very trivial example. We really did not need to introduce logs, even though the unknown was a exponent. But let's take a look at problems where we do need it. So let's say if I have something like this, I have 2 raised to 3 minus 4x is equal to 100. Okay, and I want to solve for x. Okay, now I do want to caution you, sometimes it's easier to introduce one base over the other. Do you guys follow? But if you're not sure, you can always use a base e. Okay, I always prefer to use a base e, then you're consistent throughout. let me go back to this problem for a minute. Now, anytime you're given an exponential equation, this is an exponential equation because the unknown is an exponent. Okay, anytime you're given an exponential equation, if you can write everything as the same base, then you can do this. Do you guys follow? So if I can write everything as the same base, I can do that. For example, even this, if I was given 4 raised to 3 minus 2x is equal to 4 raised to x minus 1. Since these are both the same base, that tells me the exponents would have to be the same since these are equal. So I can write it as 3 minus 2x is equal to, actually let's make it a little bit more interesting. How about this? 1 over 4 raised to, let's say, x minus 2. Okay. Now I can't compare these right now because this base is in the denominator. So I mean this exponential number is in the denominator, so I need to move it up. That's easy to do because we have a nice property of exponential numbers that tells us that if you move it to the top, you just change the sign on the exponent. So we get negative x minus 2. And I'm introducing parentheses here because I have two terms on the inside, and I put a negative on the exponent. So now these two exponential numbers are the same. They have the same base. Whenever they have the same base, the exponents will also have to be the same. So we get 3 minus 2x is equal to negative x minus 2. We know how to solve that. So we get 3 minus 2x is equal to negative x plus 2. You move all the x terms to one side. So we get 3 minus 2 is equal to negative x plus 2x. So we get x is equal to 1. Okay, so we can do these problems. The reason why we can do these problems is because we end up with two exponential numbers that are the same, that have the same base. Then those exponents have to be the same, just like over here. But majority of the time, that's not what's going to happen. You're going to end up with problems like this. I cannot write 100 as a power of 2. If, for example, if this was 128, I could have done that. I could have written 2 raised to 7, and I would be okay. All right. But in this case, it's 100, so I cannot do that. So what I'm going to do is, what did we decide to do? We're going to introduce logs on both sides, and you can introduce any base. I'm going to introduce base e, okay, which will make it a little bit longer, but then you're always consistent, then you don't have to guess what base to use. Okay. Then one of the properties of logs was what? If you have an exponent, you're taking log of an exponential number, that exponent can come out. Since there are two terms out here, make sure you guys put parentheses. Oops. Now we are solving for x. Now it's just a regular problem. Remember, ln of 2 is just a number, so is ln of 100. So these are just some numbers. We are solving for x, so you want to isolate the terms that has an x in it on one side, and then you eventually want to isolate just the x by itself. But before we do that, we always get rid of the parentheses, so we'll distribute. So we get 3 ln of 2 minus 4x, and I'll write it this way, 4x ln of 2 is equal to ln of 100. Since I'm solving for x, I want to isolate the x term on one side, so I get 4x ln of 2 is equal to ln of 100 minus 3 ln of 2. And then we're going to divide both sides by negative 4 and ln of 2 to get x by itself. So we get x is equal to ln of 100 minus 3 ln of 2 divided by negative 4 ln of 2. And there's your answer. It's a good idea to do it on the calculator, because I would like to see if you understand how to use your calculators to do these calculations. So let's take a look at that. So we want to take this thing on the top, so let's put parentheses, ln of 100, close parentheses, minus 3 ln of 2, close parentheses, divide that by, open parentheses, minus 4 ln of 2, and we get negative 3.45, negative 3.45. Can we check our answers? Of course we can check our answers, because it's an equation. Anytime you have an equation, we can check. What you can do then is, you can take this answer that you just got, there's an answer key here, if you notice answer, and you can store that into x, and then we'll take 2 raised to this number, so we get 2 raised to parentheses 3 minus 4x, and that should equal to what, 100? So let's do that. And that did not equal to 100, so we obviously did something wrong, so let's go back and figure it out. Okay, so I stored 2 raised to that, we got 4 times 4 minus x, so we got some big number. Okay. Oh, I know what I did wrong. If you notice, when I did this calculation here, I forgot the plus sign between the ln of 100, I'm sorry, the minus sign between the ln of 100 and that, so let's fix that. If you press the second key and the enter key enough times, you'll end up with your thing that we started with. There we go. So I can go up, I can go second and insert a minus key. That's better. So we get, and that's, you see, it was really good that we checked it. So we got approximately negative 0.91. I usually like my answers rounded to 2 decimal places. 0.91. So let's check it now, make sure it's right this time. So I'm going to store that into x. Then I'm going to take 2 raised to parentheses 3 minus 4x, and that should be 100. That's what it is. So we know our answer was correct. Okay. So that's how we solve exponential equations where the unknown is an exponent. Let me do one more problem that's a little bit more difficult. Let's say if you have 2 raised to x minus 3 is equal to 3 raised to 2 minus 3x. Okay, I want to solve this for x. So let's do that. My unknown is an exponent. I cannot, these two bases are not the same, so I can't compare these exponents. So I have to introduce logs on both sides. I'll use ln as my log that I'm going to introduce. You can introduce any log base. I just prefer ln for 2 reasons. One, I have a key on my calculator for it, and then the second reason is that it's easier to write ln as opposed to log of something base 2. I can take this exponent and bring it in the front. Since there are 2 terms, make sure you guys put parentheses. So we get ln of 2. Same thing, this exponent comes first. And that's where you can see whenever the unknown is an exponent, introducing logs lets you bring that exponent down so you can isolate that. Because if the unknown is written as an exponent, there's no way to isolate it by itself. So now we are solving for x, so the next thing is always get rid of a parenthesis. So we get x ln of 2 minus 3 ln of 2, I'm distributing. Same thing over here, we get 2 ln of 2, 3, minus 3x ln of 3. So we want to solve for x, so all x terms on one side. So I'm going to move this term that has an x in it there. I'm going to move this number to the right that has no x in it. So I get x ln of 2 plus 3x ln of 3 is equal to 2 ln of 3 plus 3 ln of 2. Now what do I want to do? I want to somehow combine these, and I can do that because I can calculate this and 3 ln of 3 on my calculator and add them up, but it's always a good thing to wait till the very end to take logs of stuff because of round off errors. But what I can do is both of these terms have an x in common, so I can take that out. Okay, so I get 3 ln of 3 is equal to 2 ln of 3 plus 3 ln of 2, and I can divide both sides by this because that's attached by multiplication. I want x by itself, so I get x is 2 ln of 3 plus 3 ln of 2 divided by ln of 2 plus 3 ln of 3. So now I can punch this into my calculator and get an approximation, and then we can also check our answers. We also want to do 2 things. So we get parentheses, we get 2 ln of 3. Make sure you guys, once you type in ln of 3, you have to close that parentheses for that. Then you get plus 3 ln of 2, and then we want to close parentheses for that ln of 2. And then we also want to opened a parentheses at the beginning because we needed the parentheses here and here because we want to take that big chunk and divide by that. So I need to close another parentheses. Divided by open parentheses ln of 2, close that parentheses for that, plus 3 ln of 3. And then I'm going to close that parentheses. So we get this. So let's store that into x. And let's go back up and check our answers. So I'll have to do 2 things. I'll have to plug in the left hand side and the right hand side and see if they are the same. So let's do that. I have 2 raised to parentheses x minus 3. So we get that, and then we have 3 raised to parentheses 2 minus 3x, and got the same thing, so we know our answer was right. So that's how we do exponential equations. Whenever the unknown is an exponent, you always have to introduce logs, unless it's a trivial problem like the ones I started with, these two, where the bases are where the two exponential numbers are the same with the same base. Then you can compare those. When you have two exponential numbers that are equal with the same base, you can compare the exponents. Same thing over here. Okay, but you could have done this problem, by the way, using logs. You could have introduced logs. You could have done this problem introducing logs. Okay, so you're not limited to just doing it that way. The next problem, the next type of equation we have is one log term equation. Okay, so in this case we want to use the definition of logs to write the equation as an exponent. As an exponent. That is, if you're given this y is equal to log of x base b, I can take this b and make it the base on this side, so I can write it this way: b to the y is equal to x. Because we want to solve for x, we want x by itself, so we want to get rid of the log. Because x is inside the log, so our goal should be to get rid of the log term. So we're using the definition of logs to do that. So let's take a look at a couple examples of that. So let's say if I have log of x plus 2 base 3 is equal to 4. Okay, I want to solve for x. This is a logarithmic equation, so we call this a logarithmic equation, a log equation. Okay, why do we call it that? Because I have a log term and an equality. Okay, now I want to solve for x. X is inside these parentheses, which happens to be inside the log because we're taking log of this term. So our first goal should be to get rid of the log term, and that's where this comes in, because this lets you write something without logs. It lets you write it as an exponent. So let's do that. So I take this base, it becomes a base on the other side, you can see that, and then you just drop the log. So we get x plus 2 is equal to 3 to the 4. So we get x is equal to 3 to the 4 is 81 minus 2. So we get x is equal to 79. Okay. Now this one's going to be a little bit harder to check. Not difficult, just harder. Why? Because the base is 3. I would have to do a change of base to check it. So I'd have to do this. I would have to take ln of x plus 2, because log of, let me write it properly. If you want to check your answer, this is, you take log of x plus 2 base 3 is the same thing as ln of x plus 2 divided by ln of 3 using change of base. So let's use this, and the answer should be 4. So I'm not going to check all the problems, but I'll check some of them just to kind of get you the idea. So I take ln of, oh, I'm sorry, I got to store this, 79. So you take 79, store x, and then we take ln of x plus 2, close parentheses, divide that by ln of 3. You should get 4, which is what we had, so we're good. So that's how you solve an equation that only has one log term, and it's called a logarithmic equation. Let me do a couple more examples just to get the idea across. Okay, how about something like this? Let's say if we have log of 3x minus 5 is equal to 2. Okay, out here the base is not given to us, but we know what the base is. It's supposed to be 10 when it's not given to us, right? And this is a logarithmic equation. It has one log term and an equality. So the goal is to get rid of the log, and the only way you can get rid of the log is by using this definition. Well, there's another way, and we'll talk about that, but majority of the time it's the definition. We take this 10 and make it the base on this side. So we get 3x minus 5, and you drop the log on the left, you get 10 squared. So we get 3x is equal to 10 squared is 100, and you move the 5 over, so you get 5. So we get 3x is equal to 105. So we get x is equal to, you divide both sides by 3, so we get 35. And there's your answer. Okay, and you can always check your answers, so make sure you guys do that. So once again, to check my answers, I'll have to change the base if you want to do it on your calculator. So you'll have to take log of 3x minus 5 divided by log of 10. This time, instead of using ln to change my base, I used log. The reason for that is because now the base and the number are the same, so the log of that is 1 using the log properties. So all I have to do is take the log of the top. So let's do that. So I'm using the log key this time. Log of 3 times 35 minus 5 should give us 2, which is correct. That's what we had. That's pretty much it with one-term log equations. So let's move on to the next topic. When we have two log term equations, but did I do one? Yeah, two log term equations. What we want to do here is we want to basically change this to one log term equation. Do you guys follow? So if you have an equation with two log terms, somehow we want to change it to one log term, and then we know how to solve that. We just did two examples like that. Okay, so let's take a look at that. So how do we do that? What we want to do is we want to use isolate the log terms. First we want to isolate the log terms, and then we want to use the product / quotient property to combine the log terms. So what we want to do is use the product or the quotient property to combine them into one. So now you'll have a problem with one log term, and then we know how to do that. So let's take a look at an example. I'll give you two examples of this. So let's say if you have log of x is equal to 2 minus log of x plus 15. Okay, this is a logarithmic equation because it has got logs and equality, so we know that. And then the other thing we also note is that I have two log terms, so I need to do what? Isolate the log terms on one side. So let's move all the log terms on one side. By the way, the base of this log is 10 since they haven't given that to us. Okay, then I'm going to combine these two into one. So what property of log can I use to combine them into one? Okay, so let's think about it. I have two log terms with a plus sign in the middle, so I can use the product property. So that tells me I can take the log of x times x plus 15 is equal to 2. Okay, so I combine them into one. Then what do I want to do? Well, let's continue to take a look at it. I have one log term. It's exactly like these two problems. I want to get rid of the log term. The base is 10, so this base becomes a base on this side, and you drop the log, so we get x times x plus 15 is equal to 10 squared again. Now if you distribute here, we get x squared plus 15x is equal to 100. So it's a quadratic. So you move all the terms to one side whenever you have degree 2. I'm hoping you guys remember that. And then you solve. Okay, this is a quadratic. You can either use a quadratic formula or you can factor. In this case I can factor because I can use the AC method. I get x plus 20, x minus 5. This product is 0. That tells me one of them is 0. So I get x is equal to minus 20. You get x minus 5 is equal to 0. So I get x is equal to 5. So now the question is, am I done? Well, let's take a minute and think about it. Remember what we said at the very beginning of the section on logs. The domain of the log function is everything from 0 to infinite, not including 0. That means we cannot take log of 0, and we cannot take logs of negative numbers. If x is 20 if x is negative 20, right away when I plug it in here, I get negative 20 here, log of negative 20. Can I do that? No. So that tells me that this is not one of my solutions, but 5 is fine, so we get 5. Okay, so let's check our answers just this last time, and I'm not going to check anymore. I'll just use this second line to check our answers. I want the left hand side should equal to the right hand side. So I take, this is log, not ln, log of 5. I could have stored that into x, but I'll just do it. Log of 5 plus 15 is 20. We should get 2, and that's what we have, so we're good. Okay, so that's how we do equations with two log terms. Let me do one more example of that. Okay, so let's say that we have log of x base, everything seems to have base 5 here, 10. So let me do this. I have log of x plus 1 base 2 is equal to 3 plus log of 2x minus 1 base 2. Okay, so let's solve this for x. This is a logarithmic equation. You have log and equality, so you want to move all the log terms on one side. So let's do that. Okay, so now we want to combine this into 1. Okay, so there's a negative in the middle, so we can use the quotient property of logs this time. So you take the log of the first divided by the second, should equal to 3. So now we are down to one log term. We know how to solve problems with one log term, right? What do? We get rid of the log by writing it as an exponent. So we take this base and make it the base on this side and get rid of the log. So we get x plus 1 over 2x minus 1 is equal to 2 raised to 3. We're using what we did earlier today. And now we have, this is over 1, so this is just two fractions equal. Anytime you're solving, you want to get rid of the fraction, and if two fractions are equal, the best way to get rid of them is by cross multiplying. So we get x plus 1 is equal to 8 times 2x minus 1. So we get x plus 1 is equal to 16x minus 8. So we rearrange it, so we get 1 plus 8 is equal to 16x minus x. So I get 15x is equal to 9. So you divide both sides by 15, so we get x over 15, 9 over 15 is equal to 3 over 5. So that's what we did over here. They'd asked us to solve this for x. We had two log terms. So let's go ahead and check our answers. Now this is going to be again a little bit tricky to check. Why? Because the base is 2, so we'll have to do like a change of base. Okay, to do that, to check our answers. But it is something we can do. Okay, what about 3/5? Let's go back and check if that works. I have 3/5 plus 1, so you get a positive number. Common denominator is 5 over 5, so you get 8/5, so that's good. Over here we get 3/5, so we get 3 times 2 times 3 is 6/5 minus 1, so we get 1/5, so that's a good number. So that is a good answer. And I'll leave it up to you to check it, but if you want to check it, you'll have to do a change of base. You'll have to write the left hand side as ln of x plus 1 over ln of 2. I did a change of base here. Should equal to 3 plus ln of 2x minus 1 over ln of 2. So you'll have to do a change of base to do this, but it is something you can do. Okay, alright. The next type of problem we're going to take a look at. So I did two problems with two log terms. The last one is when we have three log terms. So we have three log terms. So this time we're going to do is we're going to combine two of them. Combine two of the log terms. And then use log property the one-to-one property to write without logs. and I'll explain this. Okay. The one-to-one property was this. It said that if you have log of A is equal to log of B, in this case base is 10, the only way that's going to happen is if A is equal to B. Okay, so if you have two log terms equal, you can just basically imagine you're canceling out the logs. Okay, it's not what you're really doing, but I'm just saying you can imagine that. So, but you're using the fact that log is a one-to-one function. If this is my y and this is my y, if two y values are equal, the only way that's going to happen is if the two x values are the same, because for each x you only have one y, and for each y you only have one x, since it's one-to-one. Okay, so let's take a look at an example. Okay, so let's say if I have ln of 1 minus x plus ln of 3 minus x is equal to ln of 8. I have a log equation, I have logs and equality. I have three log terms. So I'm going to combine two of them first. So let's combine these two because there's a plus sign in the middle. We're going to use the product property. So I can get ln of 1 minus x times 3 minus x is equal to ln of 8. Now I have two log terms equal. Anytime you have two log terms equal, that tells you that these values also have to be the same then. So that tells me that 1 minus x times 3 minus x must equal to 8. So let's go ahead and solve this. I'll have to get rid of the parentheses first. So I get 3 minus x minus 3x plus x squared is equal to 8. This is a quadratic, so you want to move everything to one side. So you get x squared minus 4x minus 5 is equal to 0. I move the 8 over, so it becomes negative 8 plus 3 is negative 5, and I combine these two. I can factor this or use the quadratic formula. In this case I can factor, so I get x minus 5 and then I get x plus 1. This product is 0, correct? So that tells me what? One of them has to be 0, so you get x minus 5 is 0, so you get x is equal to 5, and I get x plus 1 is equal to 0, so I get x is equal to 1. Well, this is a great problem because a lot of the time students see a negative answer for x and they'll say, okay, this doesn't work. But that is wrong. In this case, actually this works and this doesn't work. And you have to do that by checking. If x is 5, you get what? 1 minus 5, so you get negative 4. Can I take log of negative 4? No. So that's why this doesn't work. Okay. How about x is minus 1? You get 1 minus of minus 1. So this becomes a plus 2 because you get negative and negative is positive. Out here we get 3 minus of minus 1, so you get negative times negative is 1, so you get 3 plus 1 is 4. So you can see that one works. So please don't just fall under the trap that, oh, it's a negative number so it doesn't work. You do need to check it before you make that kind of a claim. Okay. Alright, so we did that with two log terms. Let me do one more problem of that type. Okay, see if we can do one that has okay, so we have this. We have log of 5x base 7 minus log of 3 base 7 is equal to log base 7 of 2x plus 1. Okay, I have three log terms. Alright, so we want to solve this for x, so we combine two of them. There's a negative in the middle, so we'll use the quotient property. So we get log of 5x over 3 base 7 is equal to log of 2x plus 1 base 7. Is that okay? Now I have two log terms equal. Since log is a one-to-one function, that's only going to happen as if this is equal to this. So we get 5x over 3 is equal to 2x plus 1, and this is over 1. I'm solving for x. I want to get rid of my fraction. When two fractions are equal, the best way to do that is cross multiply. So we get 6x plus 3. I move this over there, the 3 on the other side, so you get negative 3 is equal to x. 6x minus 5x is x, so we get this. So now if x is negative 3, you get 5 times negative 3 is negative 15. Can I take log of negative 15? No. So this doesn't work, so this problem has no solution. Okay. Alright, so we took a look at a couple of these problems, alright, and they're kind of nice problems. You just have to practice them, get a good feel for them. Let me go ahead and do like two special problems that don't fall in any of these categories, but let's start with this one. Let's say if you have e is equal to ln of 3x plus 1 is equal to 2. How do I solve this? Well, there was a log property that said that if you have this, if you have b raised to log of some number base b, if the base of the log, which is an exponent, is the same thing as the base of the exponential number, then you just get x. You just get this back. So in this case, this left hand side, since this base and this base are the same, you just get 3x plus 1 on the left is equal to 2. So we get 3x is equal to 1. So we get x is equal to 1/3. Okay, so we just used a log property there to do that. So that's one special problem. The other one is this. We have e to the x plus e to the minus x over 2 is equal to 15. So I want to solve this for x. Now this one's a little bit tricky, and this is the last problem of this section. Like I said, I was going to do one that's a little bit different. So let's do this. This is technically two fractions equal. I want to solve for x. X is an exponent. So right away you know you have to introduce logs. But I can't introduce logs in the way it's given to me, because if I introduce logs like this, there's no log property that lets me bring this in the front because of the sum. So I'm going to be stuck. So I'm going to have to do some algebra first. But first thing is, since two fractions are equal, let's cross multiply and get rid of the denominator. So I end up with 30. Okay. So now I want to solve for x. The only way we're going to be able to do that is by somehow getting down to one term with x as an exponent, and then we can introduce logs or something like that. So let's see if we can do some algebra. This is a negative exponent, so we can write it this way. And since we have equality, I can multiply everything by the common denominator, which in this case is e to the x. Okay, so let's multiply everything by the common denominator. So I get e to the x times e to the x plus e to the x times 1 over e to the x. Anytime you have fractions and equality, we always want to get rid of the fractions. So that's what we are doing. E to the x times e to the x is you add the exponents since the base are the same. So you get x plus x is 2x. Plus out here these cancel, so we just get 1. And out here we get 30 e to the x. Now, let's take a look at it. Let's move this 30 to the left, and I'll tell you why. Because I have three terms, because I don't know how else to solve them, because I still have two terms with unknown exponent x. So I can't introduce logs yet. But I have three terms, okay? And none of the methods that I've learned so far, even logs, don't work here. So we can think about it. There was a method that we talked about a long time ago, something called almost quadratic. And that's what's going to work here. Okay, because anytime you have three terms and none of the methods that you've learned so far work, then you try to see if it's almost quadratic. How do we check to see if something is almost quadratic? You take the middle term variable, which in this case is e to the x, and you square that. Anytime you square an exponential number, you multiply those exponents, so we get e to the 2x. And if you get the first term variable, then it's almost quadratic, so it is. So then we make a substitution. If you recall, we said z is equal to the middle term variable. Then you square both sides. So we get e to the 2x. So I'm going to replace e to the 2x with z squared. So e to the 2x gets replaced with z squared minus 30 e to the x. E to the x gets replaced with z plus 1 is equal to 0. So that's how we do this problem. The next thing we want to do is what? We want to solve this quadratic, and cannot be factored, so we'll have to use a quadratic formula. So I get z, we're solving for z, so we get z is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. So we get minus of minus 30 plus or minus the square root of 30 squared minus 4 times a, which is 1 times c. Oops, I forgot minus 30 squared, I forgot the parentheses. C is also 1 divided by 2 times 1. So we get 30 plus or minus the square root of 30 squared is 900. 900 minus 4 is 896 divided by 2. Okay. So let me see, what is 896? Let's see, is it 32 times 14? No, that's not what it is. Times 2. Oh, so it's 64 times 14. Okay, so this radical can be broken down into 64 times 14. Square root of 64 is 8 times 14. So we get 30 plus or minus 8 square root of 14 over 2. And I can clean this up a little bit. Divide 30 by 2, so you get 15. You're just separating each term of the numerator. And 8 by 2, we get 4 square root of 14. So that's what z is. But remember, we were originally solving for x, so we have to change z back to x. What was z? E to the x. So we get e to the x is equal to 15 plus or minus 4 square root of 14. Now after all that work, we got it down to one term with an unknown exponent. Now we can introduce logs, but we could not have done it before, because this is an exponential equation because we have an unknown exponent. So we introduce logs, so we get ln of e to the x is equal to ln of this. Okay, you bring the x in the front, you get ln of e. So what is ln of e? Well, let's take a look at it. What's the base of this e? If the base and the number are the same, we learned in the properties of logs that's always 1. So the answer is x is equal to ln of this. Okay. Now, there's your answer to this problem. Okay. So this problem was a little bit more interesting. Even though the unknown was an exponent, we could not introduce logs right away because we had a plus sign in the middle here. So we had to do some algebra. When that happens, you just keep working your way through it. Perform as much algebra as you can so you can somehow get it to somewhere where you can introduce logs, because you know you're going to have to introduce logs since the unknown is an exponent. It's just a matter of you got to be patient with it.